All right, cool. Hello, everyone. I'm Conrad, and this is my presentation on spanning tree security, chopping down the spanning tree. You know that protocol that nobody likes? Yeah, that one. STP. It like a jealous ex is coming back. See, you thought you escaped. You thought you were done with this after routing and switching. Nuh-uh. You're coming back here, and this is going to be great. We're going to chop down these trees faster than the wrecking balls flattened Colony Manor. So first off, we'll do a quick review. The spanning tree, jog your memory. I'm sure it's been like 3 years since you took routing and switching. And then we'll go over some attack scenarios, and then how you can stop them. Also, another note is that I'll be focusing on RSTP, not STP. Nobody uses STP. If you still use STP, you're a moron. However, STP and RSTP have the same flaws, which is why it's not too much different. Something backwards compatibility. You know how it always goes. So first off, explain why is this still relevant. They've been trying to kill RSTP for years now. They've introduced trill over R bridges, shortest path bridging, MPLS, all these data center link technologies, and RSTP is still around. Not in the carrier networks though. A lot of carrier networks, Spectrum and all they're not running RSTP. Larger companies, they're not doing that either. It turns out spanning tree protocols lead to poor efficiency because what you're doing is basically disabling links. You're disabling perfectly good links on a switch that could be used for something, but instead, you got to bottleneck the entire network by turning it into a logical tree. The only cool. The only problem is that the link state protocol alternatives, such as shortest path bridging, they're really complex. And so what you get is RSTP is the Ubuntu of switching. It just works. You plug it in and it just starts working. The point is that RSTP is not going away in small companies. RIT still uses RSTP. So this is something that still gets used. They make it sound like it's not, and it still is. So refreshing your memory. This is interesting because when I first brought this presentation together, it was for my advanced routing and switching class. It's been heavily modified since then, and the reason is because it's been a while, hasn't it? Again, 3 years probably since I took routing and switching. Yeah, and some of you, did you know? A lot of the underclassmen don't even know what STP is anymore. They stopped teaching it in routing and switching. Yeah. They no longer teach spanning tree in routing and switching. So some people haven't even heard of this before. So this is why I want to explain why the protocol exists in the first place. We use spanning tree to avoid switching loops. What are switching loops? Switching loops is when you have uncontrollable broadcasts on a network. Let's say you have host A and B over here, and host A sends a broadcast frame. What's going to happen is switch A is going to broadcast that to host switch C and B. Then C and B are in turn going to broadcast those messages to each other. And then what you're going to get is this broadcast message continuing to propagate over and over and over again throughout the entire topology. There's no stopping it. The only time it ever stops is when one of the switches fails or somebody breaks the link. So we call those broadcast storms, right? And so if your reaction ain't like my man's Elmo over here when something like that happens, then I don't know. That's a little bit of a problem. I ain't doing my job right. But there's 3 major problems: unstable MAC addresses, broadcast storms, as I just mentioned, and duplicate frames. Broadcast storms are the big one. So how it all works, oh my God. I had like a 3-minute video.
Yeah, here.
Because I'm not about to explain spanning tree to...
It's valid. So what we're gonna do is this.
Oh no, that's not it. That's
That's not
the
that?
original video. I edited this one. Here, request access.
Technical difficulties again.
Yeah.
Did you trim it or something?
Yeah, I did.
Could you just go to the section, or is it sections that you cut out?
It's cropped all over the
I
place.
see.
And screw you, Google.
Oh,
There we go.
is it fine? Fighting?
No sound.
Just because it's no sound coming out of here.
Possible, I don't know.
Is it coming through the stream? Where's Jason? Oh, you come fix the sound, buddy.
So this video is just a highly edited short clip. It's from the Cert Bros, really nice channel on YouTube, and they explain what spanning tree is all about.
For the string. Well, it's not playing right now.
I was afraid this would happen.
Any audio supposed to be coming through? Then it's gonna come through this. Probably. Oh, that's pretty. Do you think you can explain what the video is doing?
Yeah, that's fine. All right, so what's going on here is we're simply blocking
Sorry.
one of the ports.
Trim process.
Yes, sir.
The video is fun. Alright, you're good. Sorry, Conrad. Sure. It's fun.
All right, cool. So here, the idea is we want to block one of the ports. This allows data from going from switch B to switch A and C to not loop. So the frame gets broadcasted, switch A in turn broadcasts that, but switch C receives the packet and it just ignores it. It doesn't actually physically rip its own cable out, it just ignores it. So that's the idea behind that, and that actually fixes it. That's pretty much it. Of course, how you do it is the big question, how switches decide what to do. So the first step is to elect a root bridge. We'll see this here. This bridge is the king or queen of switches. And this bridge has only interfaces in forwarding state, otherwise known as designated ports. And then each non-root switch selects their root port. This is the best path to the root bridge. Okay, and then remaining links choose whether or not they're going to be a designated port. So in this case, switch B has a designated port, and then all other ports are put into a blocking state. And that's pretty much it. That's a high-level overview of how the decision process works in spanning tree. And I want to focus on that first step, though, electing a root bridge, because that one's important. And that's going to be the focal point of a lot of attacks. Right. So, in order to determine the root bridge, all switches send out what's called a bridge protocol data unit every hello timer, which by default is 2 seconds. They also contain a lot of things, but among them, the path cost of the root, my BID, bridge ID, and the root bridge ID. So the idea is that the lowest bridge ID is going to win the root bridge roll. Normally, the bridge ID is going to be a priority value that's administratively set, and the bridge's MAC address. The thing about the root bridge is that it never blocks any ports. It's guaranteed to not block any ports because it's the root. So unless it has redundant links to itself, which we can get all complicated with that, but that's the idea. Root bridge is important. So now on to the good stuff. Attack scenarios. So first, before we jump in, I want to introduce a nice little tool called Yersinia. And Yersinia is actually named after the bacteria that caused the Black Death. Like, I know we're all tired of viruses now, but you know, it's like nice to have bacteria get some love every once in a while, you know? And so it implements several attacks for RSTP. And not only RSTP, but everything like OSPF, RIP, you know, Cisco Discovery Protocol, lots of things. And this is going to be the main tool that I use in the attacks. But first, I want to ask a question. True or false? The bridge ID must be the bridge priority number plus the bridge MAC. And the answer is false. All zeros is a completely legitimate BID. Not only is it completely legitimate, it's unbeatable. So now you've got all zeros as your bridge ID, nothing can beat it. And that's going to be how we will take over the root bridge role. So root bridge attacks will be centered around the root bridge, taking it over. So this is what, you know, our standard topology will look like, you know, meshed switches and whatnot. And you got an attacker with a few links. Of course, I've never seen a host with 3 links on a network before. Usually if it's a server, it's like 2 links, you know, whatever. But for purposes of demonstration, those 3 links. And then a bunch of switches, and then, you know, a client and a server. This is all in GNS3. I highly recommend GNS3 if you're using simulation. GNS3 implements communication between different hypervisors. So my server and client and all the switches are running in Docker. The attacker is running on QEMU, and Zulu is running on VMware Workstation. All in the same logical topology, communicating with each other. It's really powerful. So this is what it looks like before the attacks. The only thing is, it's like, this is what it's going to look like after the attacks. And, oh dear, who's that? I don't remember putting that there. All the switches will be compromised in some way. Now, I'll introduce you to another character of mine. His name is Hackerman. I'm not gonna lie, this guy's, you know, kind of sus, but we'll work with it, you know? It's you gotta do what you gotta do.
AirPod shoddy, you looking kind of sussy.
So the first attack on a root bridge is a single-homed root insertion attack. Here's the idea. Here's what Hackerman's gonna do. You take over the root bridge using only one Ethernet link. This is what you're gonna usually find in a lot of attacks, because chances are you're probably gonna take over a host that only has one link. We can do this with Yersinia attack 4, which is the claim root role, although it doesn't do a lot of things. Like, big whoop, you took over the root. Nice job. You want a medal? You know, attack 0 is the better way to go, because you can run this in a bash script and manually configure the parameters that you want to set, or the flags, I should say, in the frame. So Hackerman can perform a bunch of different attacks. And the thing about these attacks is that they're not mutually exclusive. You can perform multiple of these attacks at the same time for an epic deadly combo. So the first one is a STP downgrade, and then a timed root reelection attack, manipulating the timers of the hello forward, and forcing trunk port negotiation. That one doesn't actually require a root. So setting up the attack, we've got our attacker here, and we're going to be sending BPDUs to Charlie. We're not actually going to take over the switch. We're just going to send BPDUs that away, in that direction. So the first is an STP downgrade. Now, here's the idea. If a bridge only speaks STP, then its neighboring bridges must downgrade. Remember that whole backwards compatibility thing? Yeah, that's a huge problem when you're taking over as root. If you're the root bridge and you only speak STP, that's a problem. STP convergence, which is the time it takes for the topology to stabilize, is much slower than RSTP. So STP requires all topology change notifications to be sent to the root bridge. This is actually different than RSTP's decentralized approach. So it's not good when you have the root bridge as STP. The second one is my personal favorite. The timed root reelection attack. That's what I called it. It's not the official name. It doesn't really have a name. The idea is that all data transfer is halted whenever there's a root reelection going on with bridges. That data transfer stops. Now you don't notice it because it happens really fast. I mean, you know, they exchange frames pretty quickly, but it is noticeable along the wire. So the idea is to claim root, intentionally let the hello timer expire, wait for the other bridge to regain root, and then repeat the process again. Like, you send out, oh, I'm the new root, haha, and then you let the timer expire and like, psych, I'm still here, I'm still alive. It is such an evil attack because all you're doing is you're just triggering elections over and over and over again by letting the timer expire. And so I have like a little, piece of code down here that that I would run, and I would send out all zeros as my root ID and bridge ID, and then I would sleep for 6 seconds, do it again. And the impact of this kind of attack, I tested this out in GNS. 600, pings total. The first one is 20%, and then going higher to 6 seconds, it'd be 25%. It can get as high as 35% before it starts tapering off, because obviously if you send it at too high of a frequency, you're not going to get the same effect, because yeah, it's just like it's because then you're allowing windows of time where the data can go through. So I thought of another thing. What if we shortened the hello timer? By default, the hello timer is 2 seconds, but as the root bridge, you control the timers, and all the other bridges follow. So there's the hello timer and there's the forward timer. The forward timer is not really relevant, but the hello timer is. So let's set it to 1 and see what happens. It got so bad, I started seeing destination host unreachable come from the host that I was pinging from. And look at all those sequence numbers. 288, 292, 296, 299. That's terrible. All the data transfer was halted because I was constantly triggering re-elections of root bridges. And so the impact of this attack, 2 more ping tests, and I did it at 2 and 3 seconds. 60% average packet loss. That's crazy. And as my homie Phil Swift would say, that's a lot of damage. Now this attack, this one is truly evil. Here's the idea. Do you remember in routing and switching when you were setting up the switches and you saw the switch port mode was something called dynamic desirable? You remember that? Is that like it's an access, or it's not an access port mode, but it's a switch port mode. So you can put the switch in access mode, you know, .1Q mode, and other modes. The default mode is dynamic desirable on older switches. Nowadays it's dynamic auto, but it's the same idea. Cisco switches by default will try to negotiate trunk port links. So if you connect two switches together, you can theoretically negotiate a link with that. So let's try to pretend to be a switch and negotiate a link with another switch. Doing this allows you access to all VLANs that the switch is aware of. This is extremely dangerous. You probably have like a management VLAN running, you know, legacy protocols, you know, all that fun stuff. Not only that, but you can become the root bridge on all VLANs. You're not just the captain now, you're the friggin' king. And here's another one. Multi-home root insertion attack. The idea is that if we have two or more links, we can do even more damage. If you claim the root role, you can manipulate the traffic paths, the path costs, to get traffic to go in your direction. Because the lower the cost, the less likely you're going to have blocked ports. So this is the root bridge man in the middle attack, and then traffic path manipulation. So setting up the attack, I've got the same thing, except I've got the attacker looking at Bravo and Delta. Delta is by default the root bridge in this setup. So the root bridge, man in the middle. The idea is that root bridges with multiple links can easily intercept broadcast traffic. If you think of, you remember binary trees from CS, right? You've got the, you know, the top of the tree and whatnot, and it goes down. Imagine that the root is at the top of the binary tree. And you have a client on the left side of the tree, and you have the server on the right side of the tree. This is a logical tree, by the way. It's not actually, you know, physical. The client, in order to communicate with the other side of the tree, has to send a frame, and that frame has to traverse up the tree to the root and then go back down, because it's a logical tree, and you make it that way so that you avoid loops in your traffic. So broadcasts sent from one side of the spanning tree must traverse up the tree and cross the root bridge to get to the other side. This is great for man in the middle. So launching other attacks, you can drop traffic, poison ARP caches. You can set up a fake phishing page, you know, all that stuff. What, fake phishing page? That's an oxymoron. And so I just showed you attacks that were centered around the root, but there's also other attacks that you can do that do not require root to do so. And the first one is traffic path manipulation. So the idea is that switches advertise different path costs depending on the link speed. So it turns out you can advertise a very low path cost to nearby switches, which causes those switches to block ports on their stronger links. They say, oh yeah, you know, my link's strong, you know, here, you know, the root bridge, yeah, it's next door to me, don't worry about that. No, the root bridge is like 10 miles down the road, and you know, now you're forwarding traffic to a bridge that shouldn't be getting it. Other switches will block ports on their stronger links. What you can do then is throttle the bit rate on the links to create an artificial bottleneck. So just by playing around with the traffic path, you can cause some serious denial of service. And another one, this is kind of nice, is the Bpdu flooding attack. The idea is that switches tend to not have the strongest CPUs. Those are usually reserved for the routers, and the reason why is because switches generally rely on ASICs. They rely on hardware. This is why it's harder to emulate a Cisco switch than it is a Cisco router, because switches have special ASICs in them that help, so that you don't have to actually, I mean, like forwarding a frame is, you know, dead simple. Why would you implement that on a software level? That's so inefficient. So the idea is that they rely on ASICs. They probably don't have the strongest CPUs. What HackerMan can do is flood nearby switches with random bogus Bpdus. And because the switch has to keep processing those Bpdus, it's going to overload the switch CPU very fast, and it may cause it to fail. So the impact of this, I ran this on my GNS setup here with a Ryzen 5 3600, and the CPU usage jumped up from 6% to 48% within a few seconds. It can be deadly. Imagine a switch trying to handle that. It's not going to go over well. So lastly, I want to talk about some attack mitigations. How do we stop this? How do we stop an attacker from sending Bpdus? Superior Bpdus, causing them to be elected as root. And the first one is probably the biggest one, and that's Bpdu Guard. Bpdu Guard, and these are, you can implement all these on, Cisco switch. You go up to the net lab right now, you could probably run this command. Bpdu Guard puts an interface into an error disable state upon receiving a Bpdu. So the idea is you want to enable this on ports that you aren't going to plug switches into. So let's say a rogue host sends, a Bpdu towards the switch port, and it'll go into error disable. The interesting thing is that the port will remain disabled until manually re-enabled again. So you can imagine this as an attacker. Wouldn't it be funny if, you got access to someone's workstation, and then you're like, yeah, let's first send a Bpdu. Congrats, stupid. You just locked yourself out of the one workstation that you got access to because you put the port in error disabled. And so overall, this prevents false information from being injected into the spanning tree domain. Clearly, you shouldn't have, there are ports that should not be getting Bpdus. Of course, there's the downside to this is that it's all manual. You have to manually configure ports to, function like this, which means there's plenty of overhead. You're probably going to want to run, at that point, you're probably going to run Ansible to do it all for you. And yes, you can run Ansible on Cisco switches. It's pretty cool. Oops. The second one is Root Guard. Root Guard puts an interface into a root inconsistent state when it receives a superior Bpdu. And that state is basically the same as being a designated port. A designated port is what root bridges have. And it forces the interface to remain as a designated port. What this does is say, it prevents surrounding switches from becoming root. Because if you don't change your port state, if you don't acknowledge the topology change, you're going to stay as root, or effectively as root. So the idea is you want to enable this on non-edge ports. So any ports that are plugged into other switches, this is what you would enable on that. And then lastly is a Bpdu filter. This prevents unnecessary Bpdus from being sent to host devices in general. So it effectively disables STP on the selected ports. It prevents sending and receiving Bpdus. I'm not exactly sure when you'd want to use this. I'm guessing it's like a more aggressive Bpdu guard. But you connect it and Bpdus are not sent out on the port. The port will shut down when enabled on the interface. That's that. So you got some other defenses too. You've got, your loop guard and your unidirectional link detection. Let's say an attacker, tries to manipulate the physical layer. Say, turn the link into a simplex, style link where it only goes one way. You can prevent physical and logical unidirectional connections from. It's used for malfunctioning links most of the time. And then loop guard, which is kind of nice, prevents layer 2 forwarding loops, an extra protection. Switches nowadays are much more smarter than they used to be. If they sense that a loop is occurring, they'll try to stop it in some way. Of course, it's not a more permanent solution like, actually enabling spanning tree, but And so the last thing is that, well, Red is the imposter. So.
Very cool. I don't think we have time for
Josh.
questions.
You said red was the imposter, but is blue
Alright.
sus?
Stop
Alright.
naming, Brad.
What the
Yeah.
How, Conrad, how can
No
people
more
reach out to you with
emojis.
questions?
Thank you.
How can people reach